Welcome everyone. Good morning or good time of day in your time zone. Welcome back to Programming and Optimization with Intel Architecture, the hands-on workshop series. As usual, I will do a very quick overview of the class. This is our schedule, and today we are right in the middle in day 5. Earlier, we talked about Intel parallel architecture and specifically focused on programming Xeon Phi coprocessors, and then in the previous two meetings, we discussed expressing parallelism with vectorization and with OpenMP. Today, we are moving into the most important part of this training, performance optimization, and I will demonstrate a comprehensive example which will show off all the optimization topics that we're going to discuss. If you're interested in my slides, you can go to the course webpage. This is the URL, colfaxresearch.com how1509. If you already have earlier slides, you can just click it. If you don't have it, you can type it in your web browser, and there they are. So you can get the slides, you can get the code that we're playing with, and you can watch previous sessions if you would like to. Today we're in session 5, so these are the slides. If you have a hard time finding it, you can start from colfaxresearch.com in training web-based. This course is based on our book, Programming and Optimization with Intel Xeon Phi coprocessors. This is the URL for the book. It has discussions of all the topics that we discuss in the workshop and more. Also, all the exercises that we are dealing with come from this source. We are providing remote access to a number of people for practical exercises. If you have remote access, great. If you don't, but would like to have it, please please send me a request in the questions box in your interface. A few seats will be freed up today, and I will be providing access to more people. So if you don't have it and would like to have it, just send me a request in the question box. If you attend 6 sessions out of 10, we will give you a certificate of accomplishment in the fundamental level for this course, and you will join some 60 people out there with certificates from earlier workshops. Visit us at colfaxresearch.com, create an account. You will have free access to a lot of resources, including presentations, tutorials, case studies, downloadable code, a lot of resources on parallel programming with a significant focus on programming Xeon Phi coprocessors. I would like to do also a quick review of the material from earlier meetings, because we will need it for today's presentation. We are talking about Intel architecture, focusing only on enterprise class hardware, Intel Xeon processors and Intel Xeon Phi coprocessors. And throughout this course, I'm hoping that from repetition, you will be able to agree with me on the following. It is possible to write a single application that runs well on a Xeon and on a Xeon Phi coprocessor. And you can expect this application to scale to future Intel architectures. Specifically, if you use C, C++ or Fortran, and if you parallelize using automatic vectorization, OpenMP, and if clustering using MPI, then you have a portable future-proof application. The difference between Xeon and Xeon Phi that one needs to understand here is that Xeon is a parallel processor, but it is more resource rich, so it compensates for some inefficiencies in your application, inefficiencies in parallelism and memory access pattern. Xeon Phi is also a highly parallel processor, but its cores are lightweight, so it gives you cheap flops, cheap operations, if you can program it in such a way that you handle parallelism and memory traffic efficiently. So you can have a single application that runs well on a Xeon and on a Xeon Phi if it is a highly parallel application with good memory access pattern. And running on a Xeon Phi, it will give you better performance, however you wish to look at performance, better performance per system, better performance per setup costs or better performance per watt. But on the other hand, if your application is not optimized, and we will see it today, then Xeon Phi will be miserable, and Xeon might be able to do better. So this is what we will see live today. When you program Xeon Phi coprocessors, you have a choice. You can either program it as an accelerator. You start the application on the host, and then you insert directives in your code which move a part of your application to the Xeon Phi coprocessor. Or you can use Xeon Phi as a processor, as a compute node in your cluster. This is called the native programming model, and you basically start and run the entire application on Xeon Phi. When you handle parallelism, both in applications for Xeon and for Xeon Phi, it's useful to think of them as symmetric multiprocessors. They have multiple cores. Each core has represents itself as multiple logical processors, 2 logical processors per core on Xeon and 4 on Xeon Phi. All of these cores share memory, and when you write an application, you will create threads with a parallel framework such as OpenMP or any other framework, and these threads will usually occupy 1 per logical processor, will usually be distributed 1 per logical processor, or sometimes 1 per core for bandwidth-bound applications. These logical processors will share the vector unit, and they will, these threads will share the vector unit, and they will share some objects in the shared memory with other processors, and your job as a programmer is to make sure that you have enough parallelism, that you don't have data races that cause unpredictable behavior, and that you access memory in a favorable pattern. And we discussed OpenMP in the previous session. OpenMP is a parallel framework for multi-threading, which allows you to insert directives in your code where you tell the compiler, I want to create threads, I want to distribute loop iterations between threads, or I want to run this function in background as a task. However, to really get the best performance out of your application, it is important to understand where the parallelism is in your code. Usually you would parallelize it across threads as far out in your loops as possible, so that your threads have enough workload for each scheduling iteration. Click this link if you have the slides later, and here James Reinders gives his take on how to approach finding parallelism in your application. Sometimes you will find that you may need to restructure the order in which you do operations so that you can have parallelism. I'm beginning to talk about optimization, and let me present to you a slide that will follow us throughout the rest of the workshop. We call it optimization areas. When you have an application which you want to make closer to hardware so that you get the best performance out of the parallel algorithm that you have, there are 5 areas to focus on: scalar optimization, vectorization, multi-threading, memory access, and communication. In our course, in the labs, we have exercises written to target one specific area at a time. Usually, for a particular application, you will have to go through this list and put a mental check. Yes, I did this, I did that, I did what I could here, and I verified that I have scaling. Well, this is difficult, but at least I gave it a try with this or that technique, and I did what I could regarding communication. I want to point out that these are optimization areas for the following task. You already have an algorithm that solves your problem, be it a financial analysis problem or a natural sciences problem or an engineering problem. You have a numerical algorithm, and your task is to write a program that expresses this parallel algorithm in such a way that the hardware is able to execute it as fast as possible. This is not all there is to optimization. Of course, there is the big question of choosing a good algorithm. In this training, we cannot really focus on that because this is a whole other science. In this training, we only focus on making the code of your algorithm efficient in the hardware. But the choice of the algorithm is a very different story. And sometimes this involves making choices such as going with a Monte Carlo calculation versus doing a numerical differencing method. Sometimes sometimes it is a choice of which numerical method to call for handling your systems of linear algebraic equations. We are not dealing with that part of performance optimization once again, and we are dealing with a part where you have an application, you know that this is the algorithm that you want, and you're trying to make it run as fast as possible on the given hardware. Just wanted to make this clear because I think it is very important to understand what we will be talking about. As an example of an application, let's consider the n-body simulation. So this is a problem that appears all the time in natural sciences, specifically in astrophysics and in computational chemistry. The problem is this: I have multiple point particles which interact with each other using, for example, the gravitational force, or it could be the electrostatic force. It doesn't matter for computation because the mathematics is exactly the same for both of them. And unless you're modeling plasma, which has Debye shielding, the mathematics will be exactly the same for molecules and for galaxies. The way that we are going to calculate how this system evolves is we will take one particle and compute the force exerted on this particle by every other particle in the system. Then we will take the next particle and do the same. Calculate the force exerted on this particle by every other particle in the system. And in this way, we will go through all particles. For each particle, we will compute its interaction with all its peers. And we will have a total of n squared particle-particle interaction computations for n particles. This is the equation that expresses the force between two particles. You have to take particles' coordinates, calculate the distance between them as a vector, and this distance is this expression square root of the sum of squares of the differences between the respective components. And then you take the product of particles' masses or charges, if this is electrostatics, and multiply it by the distance, the position, the difference between position vectors divided by the cube of the magnitude of this vector. My apologies if I did not explain it very clearly, but I hope that this is more or less common knowledge. This is a problem that I think is introduced sometime in high school and early college. So this is the problem that we are modeling, and our task is not just to calculate the forces on all particles, but to find how these particles move in response to this force. The resulting calculation can model galaxy collisions, or planetary systems, or the evolution of cosmological structures, or if you apply it to the micro world, you can model molecules and crystals with the same mathematics. The way that we approach this problem is very simple. In fact, we have a toy model. We have every particle interacting with every other particle in the system. This is probably not the most efficient way to solve it for a huge number of particles. As soon as you have a billion particles, our algorithm will become impractical. And people have devised a lot of simplifications. Sometimes you can use a tree algorithm. You can approximate clusters of particles using the multipole expansion and use a tree algorithm, and this can give you an n log n complexity. So this is the part where you choose a better algorithm to solve the problem. But this is not our concern for this course. We are concerned with taking a specific algorithm and implementing it in the most efficient way to run on a parallel platform. I will leave the science part to you because this would not be possible to cover efficiently in a 10-day training, especially considering that we have people from a variety of disciplines joining in. So I will run my toy model of the n-body system on a cluster of 4 workstations. So there were interesting questions earlier. What is a workstation? What is a server? What is a compute node? And I thought I would introduce this because understandably not everyone may be familiar with this. So a workstation is a computer with a processor, which normally you would put under your desk, meaning that a workstation must occupy as little horizontal space as possible. So usually they are built in a tower format. A workstation should look relatively good, and very importantly, it has to be quiet. So the workstation here, you see something that looks like a workstation. It is in a tower form factor. It is nicely finished in black. And because it has so much room inside that the air going through it is capable of cooling all the devices inside the workstation even without very much fan noise. Also, because this is a workstation, sometimes it will be equipped with specific hardware such as graphics cards for video output. Now, a server is a different story. A server typically is built in a horizontal form factor, which you can put in a rack. So instead of a tower, imagine putting it on the side and you slide several of them vertically stacked inside of a computing rack. This is one difference between the server and the workstation, but another very important difference is that a server is built much more compactly. It can fit the same amount of compute power in half the volume of the workstation, which is very important for saving rack space. But the price you have to pay is that a server will typically be very, very loud because the fans must blow air through the system much faster. Also, a server will typically have less facilities for video output and possibly a different configuration of onboard interconnects to fit maybe cluster InfiniBand interconnects to fit many Xeon Phi coprocessors and so on. One of the reasons that I'm pointing this out is that Xeon Phi coprocessors that you may be dealing with, some of them are like that. They don't have a fan here, but in some coprocessors you will see a fan. If you see a fan, this is a coprocessor for a workstation, meaning that you don't have to have a huge airflow through this workstation, and the fan will keep it very quiet. The fan will only operate when you have load running on the coprocessor, and other than that, your computer will be quiet. This is a passive cooling solution. In the passive cooling solution, you must have a lot of air going through the system, so you have to have powerful fans blowing the air through. This is what we're dealing with now. So I mentioned we are going to use this this computer. This is a computer built by Colfax called Colfax ProH SXP 8600P. This is actually both a workstation and a server, so you can put it on your desk, but it will not be very quiet, or you can flip it horizontally and put it in a rack. It takes up to 4 Xeon Phi coprocessors, and it takes a dual socket Intel Xeon processor. Also, we have a cluster of 4 of these, and they are connected with InfiniBand interconnects. These are network interconnects with high bandwidth and low latency for efficient data movement. We have a cluster of 4, so each of these workstations I will consider to be a compute node. Okay, back to the n-body simulation. Sorry for the side note. I thought I would address earlier questions. The n-body calculation, as I said, we will implement an n-squared algorithm, so we'll take particle 0, and then we will have another loop that goes over particles 1, 2, 3 and computes the force on this particle. Then we'll take particle number 1 and compute the force acting from all the other particles. So we will have two nested loops in this application. And let's begin constructing the code and see where we get with performance. I have many particles. How do I store information about these particles? Let me begin with something that appeals to me as a physicist with some experience in object-oriented programming. Well, I want to make everything object-oriented, so I will try initially to create a structure or maybe a class which contains elements x, y, z, particles coordinates, and then vx, vy, vz, particles velocity components. And to store many particles, I will create an array of these structures. So what I will do is I will write a function into which I feed the number of particles and the array with particle data, and I tell it how much to propagate these particles by what time step. And then when I start running, I will record the time. When I stop running, I will record the time, and by finding the difference between these times and converting it to performance, I will to flops per second, I will compute performance. So this is my initial approach at implementing the n-body algorithm. I have a function that takes an array of particles, and it has two nested loops. Loop in line 2 goes over particles that experience force, and these are the force components that I'm going to calculate, Fx, Fy, Fz. Then I have another loop that goes over all particles that exert force. And inside of this loop, I will compute the distance, the difference between positions of these particles, and I will compute what I need for that Newton's law of universal law of gravity. I will compute r squared. I will use the softening factor to prevent division by 0, and I will then raise it to power 3/2 and use it in the denominator of that expression. So after finishing this loop, I will have computed my forces, and then I will use the forces to change particles, the particles' velocities. Notice that I don't have any masses here. I'm assuming that all my particles have a mass of 1, just choice of units. And notice that I'm using single precision. And that, again, is really, whether this is sufficient or not, really depends on the limits to which I want to make my application accurate. I have a little disclaimer. This method that we're using to propagate the particles, this is Euler's explicit method. It is known to be unstable for small time steps. And this is probably not the best method in combination with single precision, but I've tested it and saw that if I initialize two particles orbiting around each other and I use this method, then the orbit remains circular for about 100 revolutions. So not too bad, possibly not as good as I would need to simulate the formation of a galaxy, but fine for our purposes. Let's see where we get with performance. And whenever I demonstrate performance, I will demonstrate two bars, one for Xeon processors and one for Xeon Phi coprocessors. Green is for processors, Xeon blue is for coprocessors. And whenever I mean a processor, I will usually mean a high-end Ivy Bridge processor, dual socket. So I have two chips with 24 cores total. This is my Xeon, and I have a 7120p first generation Xeon Phi. I'm measuring performance in gigaflops per second. And the way that I count it is, well, I have n squared particle-particle interactions, and I assume that every particle-particle interaction is 20 flops. This is what people assume in the literature that I was able to look up across a variety of platforms, even though it's kind of difficult to calculate flops. Flops are not very well defined when you're dealing with transcendental functions. So by converting the time into gigaflops per second, I found 5 gigaflops per second on the host CPU and 1 gigaflop per second less than that on a coprocessor. This is not where we want to be. Remember the theoretical peak performance of Xeon Phi. In double precision for this model, it is 1200 gigaflops per second, and instead of 1200, I get less than 1. So we need to see where the optimization opportunities are. And one obvious fault of this application is that it doesn't use multi-threading. Well, we learned OpenMP in the previous episode, so let's try to apply it. In this application, using OpenMP is really trivial. As long as I just parallelize the outer loop using Pragma OMP parallel 4, I should not have any problem. I will not have race conditions to handle. I will not have to worry about data sharing. Every thread, different threads will work on different particles that experience force. And then when I compute the force of interaction between this particle and every other particle, I am recording it into a thread private set of scalars. So no problems with multi-threading. Because it's so easy, it doesn't mean that OpenMP or parallel programming is always easy, but it is easy just for the n-body simulation. So the second set of bars demonstrates what I got with multi-threading. The boost on the host was a factor of 25 or so. The boost on Xeon Phi was a factor of more than 100. And this is much better, right, compared to the serial code, but still far from where I want to be. I want to be an order of magnitude faster than that. And my apologies, I think I said something wrong. We are using single precision. In single precision, the theoretical peak performance of this Xeon Phi model is 2400. I said 1200. It's actually 2400. So the theoretical peak performance is 20 times greater than this. So I need to look for other opportunities for optimization. Well, I mentioned 5 optimization areas. We touched on one, which is multi-threading. Now let's focus what's happening inside of every core with respect to vectorization. And here's when I have to go back to the 1980s and take my nice object-oriented code and do something that maybe doesn't look very pleasing to somebody who's familiar with object-oriented programming. So I used to have a structure like this. One particle is stored in a structure which contains x, y, z, vx, vy, vz. Now, instead of that, I will create one structure that contains arrays. So this, for Fortran programmers, asterisk x, well, this is a pointer to an array. In Fortran, this is an equivalent of just declaring 6 arrays. One array for x, one array for y, one array for z, and so on. The effect of this change is that when I access different particle coordinates and try to load them into a vector register, instead of doing j first, x second, I'm doing x first, j second. This allows me to take 16 values of j, and when I access memory for x, the memory addresses will be contiguous. So this is the change that I did. I used to have a nice object-oriented program. There was one particle in memory, another particle in memory, and so on. And I used to have to load with a stride. So I was doing a gather operation to load 16 x components into a vector register. Now I have an array, and I'm accessing this array by index. So when I load 16 values of x into a vector register, I do it sequentially. The effect of this optimization is almost a factor of 2 on Xeon Phi and a factor of 1.5 on Xeon. This is better yet, and Xeon Phi is finally faster than the host CPU. But I would like to get some more, because this is still an order of magnitude less than what I would expect to get. So we touched on two areas of optimization, multi-threading and vectorization. Now, let's focus on what's happening inside of every vector lane. And we call it scalar tuning. So here's what I had in the original implementation. I had this power function. And I had, when I calculated forces, division by the result of this power function. One opportunity that I can recognize here is that while division is an expensive operation compared to multiplication, so if instead of computing dr squared to power 3/2, maybe I could compute dr squared to power -3/2. And then instead of divisions, I would use multiplication. This is called strength reduction, and this will already help me to speed up the code a little bit. Another opportunity that I have here is the power function is supported in hardware on Xeon Phi. But the square root function is also supported in hardware. Plus, it is much faster than the power function. And because I'm computing the power which can be expressed as a square root, I may be better off using the square root instead. Finally, one more tweak that I did here is I controlled the precision of my constants and functions. This power function, POW, is actually a double precision function. It takes double precision arguments and returns a double precision result. So when I do this computation, dr squared is promoted to double precision. Then I do the math in double precision, and then I return the result in double precision and convert it to single precision. So this is a terrible operation. To use functions that are single precision functions, I have to put a little f at the end. This is the convention in the Intel Math library. So I don't just use sqrt, I use sqrtf. This little f indicates that this is a single precision function. And so does this suffix f. It indicates that this is a single precision literal constant. This is not a problem for Fortran. Fortran is very picky about types. Fortran is not going to allow you to compile a program where you take a double precision function and feed to it a single precision number. C is different. C will silently promote your single precision numbers to double precision and then convert down. So you have to be careful with it. Also, C++ programmers do not really expect this behavior. They think that, well, the library should be smarter than that. C++ has function overload. So when you feed a function a single precision argument, it should be overloaded with a single precision implementation of this function, shouldn't it? And this is correct, but only in the namespace std. So if I had std : power, then it would be an overloaded function. But in the global namespace, there is no overload. So adding this little f makes a huge difference. So let's look at before we look at performance, I also wanted to show you something that we can do with compiler arguments to control precision. This is my compilation for the CPU architecture. And one of the arguments that I'm using here is fp model fast equals 2. This is the most relaxed floating point semantics model that allows aggressive optimizations that may not be value safe. Well, actually, the default value is actually also allowing not value safe optimizations. But for this one, for this particular application, I actually don't degrade performance. I just ignore the normal numbers. But this is what I will show in the hands-on part. The same I can use when I compile for the Xeon Phi architecture. I use fp model fast equals 2. This compiles with the most aggressive floating point optimizations. The result is pretty interesting. Thanks to these optimizations, on Xeon Phi I got 4 times more performance. On Xeon I got almost 3 times as much performance. This is good. and we touched on 3 areas of optimization: multi-threading, vectorization, scalar tuning. I know that there's 2 more areas: memory traffic and communication. So let me look at memory traffic optimization opportunities in this code. Focus on these loops that I have. I have one loop that goes over particles that experience force. One loop goes over particles that exert force. When I have a lot of particles, this loop can be pretty long. Quantitatively, I'm interested in this metric. How much data is this loop accessing? Is it accessing more than the amount of cache per core, or less? So the amount of cache per core is, in the Xeon Phi architecture, half a megabyte of level 2 cache per core, 32 kilobytes of level 2 cache per core. The measurements that I was showing to you were done with 1 million particles. Not a very large problem, but 1 million particles is corresponds to 12 million bytes read in this loop. Well, 12 million bytes is much more than the amount of cache per core. So what happens is, by the time I reach the end of this loop, so when I start this loop, I'm loading the particle data from memory into cores, and it gets cached. But by the time I reach the end of this loop, all the cached data is lost. So when I increment I and return to the beginning of J, to the beginning of the loop in J, I have to load from memory again. This is inefficient because I have caches and I'm not using them. To reuse data more efficiently, I can use a technique called loop tiling, and this is what I did here. I did loop tiling in the implementation known as unroll and jam. Instead of 2 loops, now I have 3 loops, one in II, iterating with a stride equal to 16. Another loop in J, this is like in the original loop, and the third loop in I. So I am doing all the same operations but in a different order. Most importantly, my innermost loop in I is now very short. It only has 16 iterations. So basically this is one vector iteration. So I'm loading the data of 16 particles, and I'm using them for one value of J. And then I'm taking the same 16 particles and using them for another value of J, and so on. So these particles, these 16 particles, I will reuse the data on these particles as many times as I have particles. Instead of using them once, I will use them as many times as I have particles. Well, also you can notice that instead of vectorizing in J, now I vectorize in I. This is a good thing because instead of doing reduction across vector lanes, I'm actually just storing the results in this line. But this is not what I really wanted to point out. What I wanted to point out is that I'm doing loop tiling. Instead of 2 loops, I have 3 loops, so that my inner loop is short enough. And this is unroll and jam, or another word for it is register blocking. I'm loading particle data and reusing it many times while it is still in cache, actually while it is still in the processor registers. And this last set of bars shows the performance results after this optimization. As you can see, the performance impact on Xeon Phi was a factor of 2. So Xeon Phi, another way to look at this is that Xeon Phi was not very happy with poor memory access pattern. The penalty was a factor of 2. In contrast, Xeon had a very small penalty, only a factor or less than 10%. So Xeon was able to compensate for this inefficient memory traffic with its resource-rich hardware, but Xeon Phi was not able to do that. At the same time, after performance optimization, we get much more performance on Xeon Phi, and it also helps Xeon. So this is one of the cases where you can see that you can have one code for both platforms, Xeon and Xeon Phi. And the techniques that you apply for performance optimization are the same. So we touched on 4 areas of the optimization: threading, vectorization, scalar tuning, and memory traffic. I named 5, and the 5th area of optimization was communication. And this is where this fact comes in that I can run this on a cluster. So far, I'm running on one CPU, one Xeon Phi coprocessor. But I have 4 compute nodes, 4 computers configured like this one. And let me try to scale across them. I will demonstrate this, and I will try to give as much detail as I can, but I want to make a disclaimer. Unfortunately, in this course, we did not have time to discuss scaling across clusters, and I will give you resources where you can learn more about this. So I have many compute nodes, many servers in my case. This is one compute node. It has the CPU and several Xeon Phi coprocessors. There's my another compute node, again, CPU and several coprocessors. I can take the code that runs on one CPU and insert some communication in it using the MPI framework. MPI stands for Message Passing Interface. This is a protocol for communicating between processes running on different computers which are connected into a common network. MPI allows you to do that without thinking about the fabric that interconnects your processors. It can be gigabit Ethernet, 10 gig Ethernet, it can be InfiniBand. You don't need to know whether you are using TCP/IP or InfiniBand verbs to communicate. All you do in your application when you rely on MPI is you say, I want to send this array from process number 1 to process number 2. MPI also has collective communication, and this is what I will use. There is a function called allGather, which works like that. I have an array distributed across different compute nodes. I have an array replicated across different compute nodes, and different compute nodes modified different parts of this array. And now I want to synchronize all the modified parts across my cluster. And I can call one single function in MPI that will do the synchronization. Because I'm running with coprocessors, one of the options that I have for communication is I can I can express my program in the native programming model, meaning that I put MPI processes directly onto Xeon Phi coprocessors. The hosts are not used at all in this picture. And when I communicate, communication takes place directly between Xeon Phi coprocessors. And this is what it will look like. I will have the function that moves particles, but notice that I have extra calculations here. I have n particles. This is the number of particles in the simulation. But I also compute my particles. This is the number of particles divided by how many computers, by how many compute nodes are processing this calculation. And then I'm stating that this particular instance of move particles is responsible only for this chunk of particles. So rank is the number of the processor, 0, 1, 2, 3. MPI world size is equal to 4. I have 4 compute nodes. So one processor will propagate only the first quarter of the particles. The second processor will propagate only the second quarter of the particles, and so on. And then I'm doing the same thing as I was doing before. I have this parallel tiled loop. At the very end, I call this MPI function MPI allGather. And this is the set of arguments that synchronizes array particle X across all the compute nodes. This is easy enough. I just had to add a few lines here and a few lines there, and I can scale my application across many compute nodes. But there is another approach to doing that. I can use the offload programming model. In the offload programming model, remember, you start the application on the host processor, and then you insert statements in your code, like pragma offload target mic. And these statements make the runtime library pick up parts of the code, move them across the PCI Express bus to coprocessors, and run on coprocessors. In this case, I will have to use MPI to put different compute nodes, put different processes on different compute nodes. I'll have to use to use offload to scale across Xeon Phi coprocessors, and then inside of the offload region, I will have to use OpenMP to scale across cores. The implementation will look like that. And now I will query how many coprocessors I have, and then I will divide my particles between the coprocessors that I have. I will spawn multiple threads on the host. This is what we discussed in session number 2. I will have as many threads on the host as I have coprocessors. And then I will map each thread to the coprocessor on which I want to offload, and I will begin offload. I will move all of my particles into the coprocessor and use memory retention. I will move some of the resulting velocities out of the coprocessor and some of the coordinates. Inside of the offload region, I will have this parallel loop, but it will go only through the particles that this particular Xeon Phi is responsible for. And at the very end of the program, I will have MPI communication. Here's the result. I'm showing again performance, but this time in teraflops per second versus how many processors or coprocessors I'm using. I have a cluster of 4 compute nodes. So when I was running on the CPU, remember one CPU gave me 500 gigaflops per second, so half a teraflop per second. I was able to scale to 4 CPUs with nearly 100% efficiency, and I was getting 2 teraflops per second from my cluster. Well, not bad in relative terms, 2 trillion floating point operations per second. But I also have Xeon Phi coprocessors in the system, and their performance outshadows the performance of CPUs so much that I can just run my entire code on Xeon Phi and forget about CPUs. First, I tried the easy way. Just use MPI, and this blue line shows what I got. So I scaled first across 4 compute nodes using 1 Xeon Phi per node. And then I scaled across 4 compute nodes using 2 Xeon Phis per node, 3 Xeon Phis per node, and 4 Xeon Phis per node. Eventually, I'm running on 16 Xeon Phi coprocessors, getting 20 teraflops per second. So this is an order of magnitude more than I was getting from my CPUs. And I'm using the same exact code. Literally, the same exact code down to a single line. The same code on the CPU and on the Xeon Phi coprocessor. I'm just running it differently. Well, an order of magnitude difference is good, and 20 teraflops per second also sounds good. But if I compare it to the linear scaling, I find that I'm only 76% efficient. This is because part of the time I have to communicate data between compute nodes. And I chose a problem size of 1,000,000 particles. And I did not change the problem size between different sizes of the cluster. So this is called strong scaling. If I chose a bigger problem, well, I could possibly get higher efficiency, but I just kept it here to illustrate that there is opportunity for performance optimization in software. This red line is my optimized code, where instead of using just MPI, I use MPI plus offload. Using this offload allows me to express traffic in such a way that I use parallelism in my networking more efficiently. I only communicate between 4 compute nodes instead of 16 Xeon Phi coprocessors. And when I offload from the CPU to Xeon Phi coprocessors, I use the entire PCI Express bus in each compute node most efficiently. So this allows me to attain as 92% efficiency instead of 76% efficiency for the same problem size. And this is 25 teraflops per second. So this is the 5th area of optimization, communication. Sometimes to optimize communication, you need to worry about masking communication behind computation. Sometimes you need to worry about choosing a good data traffic pattern, such as offload versus MPI. And of course, all of the optimizations that I've demonstrated are optimizations that make your parallel algorithm closer to hardware. So we have learned how to write a program that expresses your algorithm in the most efficient way. In addition to that, as I mentioned earlier, there is the big topic of choosing a good algorithm. And the algorithm that we had for the n-body simulation is a toy algorithm. It has an n-squared complexity. Uh, but with some approximations, you can really reduce the complexity of this algorithm, and there is much more opportunity for performance optimization there. So we talked about 4 areas of optimization that are concerned with running on one compute node, one symmetric multiprocessor. Multithreading, what happens across cores. Vectorization, what happens inside of each core across vector lanes. Scalar tuning, what happens inside of every vector lane. And cache traffic optimization, how your cores communicate to memory. If you are scaling across multiple compute devices, many CPUs or many coprocessors, then you also need to worry about communication, the 5th area of optimization. For the n-body simulation, we achieved 76% of theoretical peak performance with these 4 optimizations on one compute node, and then we achieved a 92 parallel efficiency of scaling across a cluster of Xeon Phi coprocessors. But in both cases, we used the same code, the same optimization methods for CPU and for the mic architecture. And I expect that this code will also scale to future generations of Intel parallel platforms, and it will also run on other types of platforms which have multiple cores, vectors, and cached memory. So this is a toy model. In this toy model, we used an n-body algorithm that has an n-squared complexity. We replicated the entire dataset across many particles. Well, it made sense because our dataset was only a few tens of megabytes in size. But of course, in realistic applications, just making a disclaimer, when you have billions of particles, you will probably split up the dataset between compute nodes, so communication will be much more complicated. And you will probably use a tree algorithm so that cache traffic tuning will be much more complicated. At the same time, what we did remains the basis of the more complex simulations. I think I've shown this earlier, but because a picture is worth 1,000 words and I have 24 pictures per second, I thought I would show this demo again. This is an n-body simulation in action. How about this? Yay, full screen. And play from the start. And let's do it in high quality. I don't know how much of this high quality probably is. This is enough. I hope that most of this high quality will make it down the pipe to you guys, but let's see what happens. And this is a very old server that we had back in 2012, but this is how old this video is. Same code on both platforms. This is the key message of this demo. Okay, thank you for your attention on this one. And I want to finish up with a couple of minutes to demonstrate some more case studies that you may be interested in. We've done a case study again back in 2012 on an astrophysical code called heat code, and I've demonstrated earlier uh, this plot. The story was that we began with an application that we wanted to speed up on the Xeon Phi coprocessor. We ported it to Xeon Phi, and the performance was an order of magnitude less than on the host CPU. When we started optimization, some optimization was more algorithmic. So as I mentioned, we were able to choose a better way to approach this problem, and that gave us almost an order of magnitude speed up. But other optimizations were making that algorithm closer to hardware, optimizing multi-threading, a scalar aspect of computation vectorization, memory access, and communication. Eventually, Xeon Phi started running a factor of 200 faster than the original code on the CPU. But the same code executed on the CPU gave us, well, the same story, 100x speed up. Xeon Phi implementation still paid out because we could use the CPU together with two coprocessors for an effective speed up of, well, 600 with respect to the original code. But this is all performance optimization. If you would like to see details, this paper talks, well, I have this these slides of these presentations, and they link to a paper. The paper discusses all of the techniques that we had to do for performance optimization, and they are in the appendix. So a lot of information here. I have a video for it, don't I? Yes, I do. This is an astrophysical calculation that was used to compute the emissivity of cosmic dust in the Milky Way galaxy, which allowed us to constrain the parameters of the three-dimensional model of the galaxy using two-dimensional sky surveys. And this is before optimization. This is after optimization on the same CPU. And this is the same optimized code running on a Xeon Phi instead of the CPU. The claim here is that optimization made the difference between a project impossible and the project possible. Another case study that's interesting is a fluid dynamics example, where we collaborated with Clifford Addison from University of Liverpool to optimize this shallow water equation solver. The interesting part of the solver is that it was originally designed in 1984, and even though it is old, it was modernized by Clifford Addison in the 2000s. But the code knew nothing about Xeon Phi. Still, he was able to recompile it and run it on the Xeon Phi for a good speed up on just one platform. And then we collaborated on scaling this code across multiple compute devices. For example, here we are running it on a CPU together with two coprocessors in a workstation, and we are getting a speed up of 2.7. This just demonstrates that if you are using high-level frameworks such as OpenMP, MPI, and vectorization, you can have a really future portable code that will run on different platforms. And again, this case study comes with a paper that you can download. I will show it in a second. The link will appear in a second. But the same code for the host and for the Xeon Phi coprocessor. This is a trade show presentation, so it showcases one of the workstations that Colfax makes with Xeon Phi coprocessors and Haswell processors. And the link to the paper will appear on the next page. Yep, this is the link to the paper. And probably have the link to this paper in the slides. Yes, I do. And one more case study that could be interesting is a Monte Carlo simulation that demonstrates heterogeneous clustering. In this case study, we created a synthetic application that performs a Monte Carlo simulation. The purpose of the simulation is to simulate Asian option, is to do risk analysis for Asian option pricing. But if you're doing natural sciences, you can still relate to it. We are doing diffusion with a drift using Monte Carlo. And in this code, we wrote it in such a way that it knew nothing about Xeon Phi, but it was able to scale and auto-balance across a cluster of CPUs. And then without code modification, we were able to scale this code across a cluster that has both CPUs and coprocessors. This is again a demonstration that future-proof optimization methods can be are not that non-trivial. So we had a code that was capable of running on a cluster of CPUs, and we were able to run it on CPUs and coprocessors for a total performance increase of 4x. And the number of lines of code that we had to modify is 0. Well, this is a synthetic application written in such a way, but we saw in the previous case study that real applications can actually also have this behavior. The key here was configuring the cluster in such a way that coprocessors share the network with the CPUs and having a BOS worker model for load balancing across CPUs and coprocessors. But first we run on processors only, and the code seems to know nothing about Xeon Phi coprocessors, and here it actually is not using them, but this is our baseline. We are and then we are running it only on coprocessors in the cluster. I believe the bottleneck of this calculation is the generation of random numbers. This is not a trivial task to do in parallel. Excuse me. And finally, the same code executing heterogeneously on coprocessors and processors. This paper also has, this case study also comes with a paper with downloadable code. The code that comes with the paper is a little bit difficult to read. We tried to make it plain and simple, but it's a question of the preferred style. If you find the code that comes with the paper difficult to read, this code is actually now present in one of our labs. So the labs that we have in the book and on your training servers, there is a lab for Asian option pricing. So we talked about 5 areas of optimization today, and I will demonstrate them again live in the hands-on part. But we will continue the course by discussing in the next session scalar optimization and vectorization. So we will revisit vectorization, this time focusing on performance. Then we will have 2 sessions about multi-threading optimization, 1 session memory access. We will not really discuss communication, but I will, in the 1 week of remote access following the workshop, I will send you all emails with suggested labs to do to learn more about this. At this point, I am ready to switch to the hands-on part. If you have any questions, feel free to type them into the question box while I do this, and I will mute the microphone for 2 minutes. So stay tuned, see you in 2 minutes. Alright, welcome back. I am ready to start. And if you are connected to your training server, you can go to Labs and then Chapter 4. This is the chapter on optimization. And I'm starting Lab 401 Overview and Body. So the demonstration that I did with the N-body simulation in the first hour, now I will attempt to do it live. Hopefully it's going to work. As usual, in this lab I have the code with which I'm going to experiment. I have a makefile and instructions. So instructions guide you through this lab, and I remember them, so I will not open this file. The makefile has a target to just build the code. As you can see, it compiles it for the CPU, and it compiles it for the Xeon Phi, as you can figure out in the native programming model. The result of running the makefile is that I have these two executables, and to run them, I have targets in the makefile. To run on the CPU, I can type make run -cpu, and I can type make run Mike if I want to run on Xeon Phi, and it will do all kinds of setup for that calculation. Well, I'm going to let this calculation run because I know it's going to take a while. And while it's running, I will open my text editor and go to the code. So let's look at what we are dealing with. I have that code that I demonstrated earlier. I have this function that moves particles, and each particle is described as a structure containing particles' coordinates and the particle's velocity components. And I have a function that propagates particles by time step delta t, or here dt. It has two loops. One goes over particles that experience force. This is the force that I'm about to compute. Another goes over all particles that exert force. And here I have the softening factor, I calculate the difference between the two particles. I find dr squared, raise it to power 3/2, and using it in the denominator of my expression for Newton's law of universal gravity. Let me show you that expression once again in the slides. This is the expression that I'm computing. I'm computing this for every particle interaction, and then I have a sum over all particles, and I'm doing this for different values of I. So let's see how my application on Xeon Phi is doing. It is not doing very well. It seems to be stuck. Let's see if it's actually running. So I'm running Mike SMC. Let's see what's happening on Xeon Phi number 1. Yes, one core is crunching away, but the performance that this core is giving me is probably not enough to do it in any satisfactory time. So while it's running, here's the first result out. It took almost 2 minutes to make one time step with 65,000 particles, and the effective performance is 0.7 gigaflops per second. I get this performance by dividing how many particle-particle interactions I did times 20 by dividing it by the time. So this is the calculation of gigaflops. Yeah, so I take the time and have this conversion factor between time and gigaflops per second. I'm going to create a log so that we can track our performance. And as usual, the log will be code, and then CPU performance, and then Xeon Phi. And let me record something. So theoretical peak performance and the theoretical peak performance of the many core architecture. So the CPU, what kind of a CPU do I have? Let me stop this. I will press Ctrl C. It will cause me some trouble down the line, but this is intentional. I pressed Ctrl C to stop my calculation because it's taking so long. And now let's look at my processor. My processor has 12 cores. The architecture is V2. Xeon V2 stands for the Ivy Bridge architecture. And this is not enough information. How about this? This is more informative. Yeah, so I have 12 physical cores. Each core is clocked at 2.6 gigahertz. And the instructions that I support are these. Well, I want to focus on whether I have AVX or AVX2. On your servers, you probably don't have either. What you will find is that you are supporting SSE 4.2 in your virtualized processor. But for me, I think I should be able to find AVX. Yes. Okay, so that's what it means. I have 12 cores clocked at 2.6 gigahertz per second. Just gigahertz, not per second. And each core has a vector unit. In the AVX instruction set, this is 8 lanes per vector. For you guys, this will be a factor of 4 instead of 8 because you're only supporting SSE 4.2 in your virtualized CPU. And I think I have to multiply it by 2 LUs per core. This is, I think, how it's going to work. And let me do the math. 12 times 2.6 times 8 times 2. This is not realistic. 8 lanes per vector. So I'm not sure about this factor of 2. 12 cores. Let me take back this factor of 2. I think I'll figure it out later. But my calculator tells me then 12 cores times 8 lanes per vector times 2.6, 250. On the Xeon Phi coprocessor, I have 57 cores times, I think 1.1. I need to run mic info. 1.1 gigahertz. And I have 16 lanes per vector, and you guys also have 16. So I should be getting, and here I have to use the factor of 2. This is for the FMA. So Xeon Phi supports fuse, multiply, add instructions, and a lot of my calculation is actually fuse, multiply, add. So not all of it, I have a square root, but there is a lot of fuse, multiply, add. So 57 times 1.1 times 16 times 2 is 2000 gigaflops per second. And my original code on Xeon Phi gave me 0.7 gigaflops per second. So I'm very far from where I want to be. Now let me check on something. if you guys are in a text terminal, you can run mic smc -c. This will show you core utilization on your coprocessors. And specifically for my coprocessor, I want to see if this application has terminated or not. Looks like it has. So in the graphical user interface, you can pull up this. Yeah, it looks like when I pressed Ctrl+C, it killed the process on Xeon Phi, so I'm not complaining. I was worried that the process might still be running. Okay, let's benchmark on the host now. Make run CPU will run it on the host with the same number of particles. It will still take a while, but we will wait for it. While we are waiting, we can do something useful and go view the system load. So on the host, I can see that I'm only using one thread. Some questions came in. I want to address them. One question is, what about dual issue in mic? Should it give you double the gigaflops? So as I mentioned, Xeon Phi cores are dual issue. There are 4 hardware threads per core. Each hardware thread fires every other cycle. So every cycle, 2 hardware threads are firing an instruction. Should it give you twice the performance? The answer is no, because they are firing 2 instructions, but these instructions can be memory access instructions or arithmetic instructions. If they are arithmetic instructions, we have to remember that all hardware threads are sharing the same vector unit. And the vector unit processes 1 instruction per cycle. So it is shared between different hardware threads. It processes 1 instruction per cycle, which actually produces 2 arithmetic operations per second, because if you're doing FMA, it's done in 1 cycle. So this is the accurate calculation. This one I'm sure of. Xeon is a little bit more tricky because Xeon pipelines are such that even though it doesn't have FMA, you can load the pipeline in such a way that you do additions and multiplications almost in parallel. It's not a factor of 2, it's a factor of 1.4. We have a paper about this. If you search for pipeline, yeah, there's a paper that shows that if you're doing a bunch of multiplications and followed by a bunch of additions, this is slower than alternating multiplications and additions. I need to log in to get to this paper. So it is a little confusing to me estimating the flops on Xeon Phi. So yeah, the paper is old, but I think it still works. Yes. So basically, if you're doing this, a lot of multiplications followed by a lot of additions, versus that, additions alternating with multiplications, you shorten the runtime by about 40%. So somebody just wrote a question about FlexLM license issue. I will address it after the webinar. I think we need to troubleshoot. Okay, so the CPU performance unoptimized with 5.8. Okay, finally, let's start optimizing. Going back to my code, I know that I was using just 1 thread, and this is the lowest hanging fruit for optimization. Where should I parallelize? I could parallelize here, or I could parallelize there. I wouldn't want to parallelize here. Why? Because if I parallelize across threads here, then every time I increment I, I would have to go back, stop all threads, and then start all threads. Well, thread machinery is actually kept hot, but I will have to parallelize. I will have to start and stop parallel loops, which incurs some overhead. Also, I will be parallelizing across a tiny fraction of the total workload in my application, and I will have to have vectorization coexisting with multi-threading. So I would rather parallelize here. And the lesson from the previous episode is that we have to put pragma OMP parallel 4. I will also put schedule guided just in case. And recompile. When I compile, if I'm using OpenMP, I have to make sure that I use the argument -q OpenMP, and this is actually built in. So let's run on the host CPU. This looks slightly better, but because it doesn't, well, let's go to the log. So OpenMP on the CPU gives me 56 gigaflops per second, and on Xeon Phi it gives me 102. Let me also try to optimize the number of threads and thread affinity. This is what we will focus on in session number 8. And learning from the lessons of the previous episode, let's try OMP-num threads. I will set it to 12. Actually, no, I will just set affinity so far. I set it to compact on the host. Does it improve performance? Oh, looks like I have OMP-num threads already set. Let's unset OMP-num threads. You don't have to do this. I just have this terminal open from the previous broadcast. So with affinity optimization, I have either 71, or let me try a different approach. One thread per physical core and 12 threads. This seems to be slightly worse, so I will go back to the original plan. I will do the same on Xeon Phi. So double check. On the host I'm getting 72, 71. On Xeon Phi I will get now, no, it's still 102. So I will set KMP affinity. This is binding of software threads to cores. 71 on Xeon and 102 on Xeon Phi. So what is the speed up that we wanted, and what did we get? On the host CPU, the speed up is 71 divided by 5.8. This is 12. So this is the ideal speed up that we wanted to get, and we got it. What about Xeon Phi? We got 102 divided by 0.7, 145. Remember from the previous episode that we expected actually to get 57 times 2. because because when I use one thread, I'm actually using every other cycle. This is 114. So we are actually getting more than linear speedup, but I think this is just because this baseline measurement is not very accurate. So we are good enough with multi-threading. That's the bottom line of what I wanted to say. Let's go back to the code and see what else we can do. What about vectorization? What about what's happening inside of every thread? So going back to the code, I can find that it is quite a bit crippled. See, here I'm using divisions instead of possibly using multiplication. So how about I rename this dr to power 3 halves to dr to power negative 3 halves, and use minus here and use multiplication there. This is scalar optimization. And I forgot to put the negative right here. This actually worked worse on Xeon Phi and on the Xeon, and difficult to convince you that this was a necessary step before the final result. But let's do one more operation, and then we will see that it was, oh, did the wrong thing. So you can see that it works better on Xeon Phi but worse on Xeon. I want to fix one more thing here. I want to fix, first of all, instead of using the power, I want to use the square root. And I will actually use 1 over the square root. And I will call it dr reciprocal. And this will now be computed as drr times drr times drr. So now this is better on the host CPU. And it is also better on Xeon Phi. So let's record these results. What I did is I replaced multiplication with division, and I replaced the power function with the square root. And so I got on the host 131, and on Xeon Phi I got 183. Now let's do one more step. If I look in the optimization report, do I have the optimization report? Hopefully I do. Let's see if I have the report for line that contains this loop. So this loop is in line 33, and let me search for line 33 here. Probably not enough information. How about I change the makefile, and instead of qopt report, I said qopt report equals 5. This is not what I wanted to do. I wanted to do make-b to really recompile everything, and this will produce a new optimization report. And now let's look for line 33. Is that all? I may be mistaken regarding how it works, but let's see. So what if I do this? Instead of 1 over the square root, I will type 1, 0f over the square root f. Is it going to improve performance? No, looks like the compiler already picked this up. Yes, um, the problem here is that the square root in Xeon Phi is supported only for single precision. So I think at the precision that we had, the compiler already optimized this to be a single precision square root. But let's keep it this way because this is the correct way to call this function. One more aspect of this calculation that we can optimize is we can set relaxed precision by editing the make file and adding a compilation flag fp model fast equals 2. And when I recompile, the host performance doesn't change, but the Xeon Phi performance gave me a few percent more. So I will record this. And now let's evaluate. On Xeon Phi, I'm an order of magnitude behind where I want to be. So what should I focus on next? I think this has to be vectorization. And regarding vectorization, I have a really quick test that I can do to see if I need to worry about vectorization or not. And the test is to go in the make file and to disable vectorization. And this is what I will do. fp, I will set no vec and also no simd. These two arguments. They will disable vectorization, but keep other optimizations the same. So now let's recompile and see how much performance I'm going to lose. I expect to lose 8x in performance on the host and 16x performance on Xeon Phi if vectorization works well. For you guys, it's 4x on the host and 16x on Xeon Phi. So let's see. No vectorization, no SIMD. On the host gives me 40 gigaflops per second, and on Xeon Phi 83. So speed up of vectorization was actually something like 3.3 on the host and something like, well, let me do the math. Yes, 3.3 and 192 divided by 83. 2.3 on Xeon Phi. But I expected a speed up on the host to be a factor of 8 and on Xeon Phi to be a factor of 16. So because vectorization does not matter that much for the code performance, it means that either vectorization is not implemented very well, or I'm not bottlenecked by vectorization, which means that I'm bottlenecked by the memory access pattern. To see what's happening, I will refer to the optimization report. And in the left-hand side, I have the code. In the right-hand side, I have the vectorization report. So the loop that's supposed to be vectorized is in line 33. And let me look for this loop. In line 33, it says, well, it was inlined. Well, very good. So what do I do about this? Oh, automatic vectorization was disabled, so there is not much that vectorization report tells me. So let me re-enable vectorization and recompile and take another look at the vectorization report. I use -B so that I really recompile, even though I didn't change the source files. So this is the vectorization report. Loop in line 33. It says loop was vectorized, and then I want to read it till the end. It says masked strided loads, heavyweight vector operations, lightweight vector operations. Yes, and it also quotes to me that potential speed up due to vectorization is a factor of 5. We actually measured a factor of 3. But this is the red flag that I was looking for. Strided loads. I also want to look at the optimization report for the Xeon Phi architecture. And it says gather was generated for the variable particle something something strided by 6 in line 39. Another gather in line 40. So a total of 3 strided loads, in other words 3 gathers. So this is the problem, these 3 lines. And these 3 lines have access to particle j of x, particle j of y, particle j of z. The way that you access memory is exactly how this diagram shows. Remember this diagram? What we are doing now is we are reading x from memory here, x from memory there, and we're reading 16 of them and loading into one contiguous vector register to do the math. I will try to modify my data structure so that I will load sequentially. And this will get rid of gathers, and hopefully this will speed up the vectorization. This is not a trivial problem, but I've done it several times, so I will do it live. If you're not able to follow up with me, well, don't worry, you will have time to do it again. So instead of doing that, I will create a new type of data structure. I will call it particle set type. And this data structure will contain an array of x components, an array of y components, array of z components, and the same for vx, vy, and vz. So my function now will create a particle set type. Well, I'll just take it by reference. The most important change is that now instead of doing j first, x later, I will do the opposite. So a little bit of Emacs magic with columns. So that's what I did. I do x first and then j. The result of it is that when the compiler vectorizes this loop, it will split it up into chunks of 16 iterations. For 16 values of j, the 16 values of x are contiguous in memory, and that's what I want to do. Well, maybe so you can follow along with me, I will stop the Emacs magic and do it slowly. Now, where else do I have to change? Here I have to change. Right. And here I have to change. And here I have to change. As you can see that this optimization is not very friendly to the programmer in that you have to go through the entire code and change how you access data and how you allocate it. Also here, I can no longer do this. I will just do this, and then I will do particle.x will be array of type float of size and particles. And the same for y and z. And the same for vx, vy, and vz. then I can no longer use this random number generator to initialize all particles at once. I will have to, let me comment this out and make a copy and do it like this. I will generate this many random numbers at a time, and I will just initialize the x component separately, the y component separately, and the z component separately. And I only hope I don't introduce bugs doing that, but we will know soon enough. So I also hope that this whole thing will be worth it. So particle, I don't need to change anything here. Yes, I need to change this. So I think this is all of the changes I had to do. And I hope it doesn't compile on the first attempt, because that would indicate that something is wrong. Ah, perfect. I forgot the dot. And particle type should be particle set type. Okay, so now it compiles, and this is the moment of truth. How much performance did we get doing that? We converted from this data structure to that data structure. Actually, before I even run, let's double check on the optimization report. I want to go here, run make, and double check on the vectorization report. So now this loop is still in line 37. Actually, no, it's in line 37, but not still. Now it has remarks about unaligned access, which actually is not important here. Unit stride loads, this is what I have now. No strided loads. This is what I was trying to get. Strided loads is a problem. Unit stride loads is good. So in the Xeon Phi vectorization report, I have, well, unaligned access. Well, fix it later. Unit stride loads, no gather. Perfect. So now it should work. On the host, I get 250 gigaflops per second. This is huge compared to the previous attempt. What about Xeon Phi? This is also not bad. So good that I suspect that I did something wrong. Oh no, this is time for this performance. Yeah. Okay, let's record this. 250 and 944. So I changed particle I.x to particle .x of I. Another word for it is structure of arrays. Array of structures was converted to a structure of arrays, and the result was 250 gigaflops per second on the host, and I already forgot, 944 gigaflops per second on Xeon Phi. The vectorization report also points out a lot of issues with alignment. In fact, this is not very important for this application, but let me fix it. Well, no. Considering the time that we have left, let's not fix it. It doesn't really affect performance. These arrays are quite large, so whenever I allocate these arrays, they will be placed on a brand new virtual memory page. So alignment is actually guaranteed. So I've optimized threading, vectorization, the scalar aspect of calculations, And I hope that now, without the nullVec flag, I will get a decent speed up. I mean, a decent slowdown. This is what I want. So the host now gives me 39 gigaflops per second, and Xeon Phi gives me 72. So the speed up due to vectorization is 250 divided by 39. 6.4. So this is much better than before, but still not 8. We wanted 8. And speed up due to vectorization on Xeon Phi is 944 divided by 72 is 13. Much better than before, but still not where we want to be. So more optimization is required, and the next hardware subsystem which we want to optimize is the memory subsystem. And for this, we have to focus on the inner loop. So the inner loop has 65,000 particles. This corresponds to 3 quantities per particle, 4 bytes per quantity. How many bytes is this? 0.8 million bytes. And we have 0.5 megabytes of level 2 cache per core on Xeon Phi. So this loop is too long. By the time I reach the end of this loop, I have lost the beginning of the data. And to exaggerate the problem, let me actually edit the make file and change the number of particles to something greater. This will make it more fun, and it will make our optimization results more pronounced. So just a second to get the new baseline. So it should take for 16 times longer, something like 20 seconds. Oh, I forgot to re-enable vectorization. Let's do that first. So recompiling, and this time vectorization is enabled. Did we recompile? Strange, we didn't seem to recompile the CPU executable. Okay, how about now? Yeah, about the same performance with a greater number of particles. 250. and this should be much faster. Yes, actually, see, with the greater number of particles, our performance dropped. So let's record. And our performance dropped because now we have even more data traversed in this loop. So the pressure on the caches is even greater. So this is where we need to realize, we are going into large problems. We need to optimize memory access. And to optimize memory access, I will use this technique called loop tiling. Do I have time for it? Possibly. If I don't do it in the time that I have left, I will give up and go to the solution. To tile this loop, I will apply a technique called unroll and jam. So I will introduce a new variable, and this is a tuning parameter of my application, but I will make a reasonable initial pick. The initial pick is something that's a multiple of 16. I will start with 16. So I am strip mining the loop. So now instead of having one loop, I have two loops. And this essentially gives me the same exact application. But let me move this loop over here and get all the parentheses, right? So far it is the same application, but what I want to do is I want to permute the inner two loops, this one and that one. That makes the innermost loop, the vectorized loop, very short, so I'm going to do a lot of data reuse. And to make this application correct, I now have to turn this into an array. I am initializing them, fx, y, and z. So these will be components of forces on particle number, on the 16 particles. And I'm going to go through all of the particles that exert force. And when I compute this, I will do this. This will be I minus II. This is just ensuring correctness. All I did for memory optimization is I permuted these two loops in J and I. Right, so I've computed the forces. And now here I will use array notation. So I will assign 16 at a time. And that seems to be it. Does it compile? Does it run? I find that it is very difficult to get this right on the first attempt. I want to double check. So this is the innermost loop. This is where I vectorize. I record and possibly what I have to do now is maybe I need to declare this an aligned variable. because now I have these short loops that are supposed to be vectorized, and I can probably declare this an aligned loop. We will focus on this hint in the next session. Do I have a bug? Oh, I have a bug, so this should be, yes. I apologize for slightly going over time, but we are almost done. This is correct. So the performance dropped slightly on the host. I'm hoping that it improved on Xeon Phi. Oh, I have a bug. 16. Multiple 16. Does anyone see the bug? VX. Unfortunately, I do not see the bug right away. Tile. Maybe get rid of this. Yes, but we see improved performance on Xeon Phi. That's where I was getting at. And apparently we did have to do alignment in those loops before I could promise it. But some additional playing with this system, and we could get to better performance both on the Xeon and on Xeon Phi. And I think it requires loop unrolling. You can go to, so this is our latest achievement. You can always go to solutions, and inside of solutions refer to instruction 4. This is where the loop tiling is done really well. Thank you very much for your attention. I apologize for going slightly over time, and I hope this was a good motivational exercise demonstrating all of the areas of optimization on which we will touch on, later in the course. I hope to see you tomorrow again, where we will talk about optimization of vectorization and all these things like attribute aligned and pragma vector aligned and alignment of arrays on the heap, regularizing of vectorization pattern. All of this we will discuss tomorrow. If you have any questions, I will be online for a few minutes after ending the webinar, so you can type in the question box. Otherwise, see you tomorrow. Thank you for your attention. Bye.